Hello everyone, today I will be solving problem 4.28 from Introduction to Electrodynamics by Griffiths. The problem states two long coaxial cylindrical metal tubes, one of inner radius A and the other one of an outer radius B, stand vertically in a tank of dielectric oil, which has a susceptibility chi E and mass density rho. The inner one is maintained at potential V and the outer one is grounded. So to what height h does the oil rise in the space between the tubes? To find h, we would need to first find how the capacitance depends on it. To start off, we can state that this oil will experience two forces that are balanced. So first will be the force exerted by gravity, and the other one would be the force, the electric force on the dielectric. So we can start off with this by first finding what the electric force on the dielectric is. And this can be found using, so 1/2 of the potential squared times the derivative of the capacitance with respect to h. So how do we find that capacitance? Well, we can find the potentials that are on the two sections. So we can see that there will be two different potentials due to there being oil inside the tubes, and then there's just a vacuum on top. So to find the potentials, we can use Gauss's law. So for the air portion, we can just draw a Gaussian surface. This would have radius s, and then we can, well, I have solved for this in the past. I could refer you to the video from problem 2.22, and you will find more specifics about how to find this electric field. So I will just be writing it down. All right, and to find the potential, we can use just the negative path integral. Okay, and now for the part that has the electric oil in it, we can still use a Gaussian surface, but because there is oil in there, we can't just use the same equation. But for this cylinder, for this surface, we would have to use this version of Gauss's law. Okay, so this is basically the integral of the displacement times the area, and then that would equal the actual charge enclosed. So in this case, the displacement is just going to be constant, and then the area that we are integrating over is basically the area of the cylinder. We can call, let me see, where did it go? Okay. We should call the length of this Gaussian surface L. So that would give us and then the charge enclosed on this Gaussian surface, it cannot be the same lambda as on top because they're different, and we will call it lambda prime, and then the length is L. So what happens is that the lengths of the surface just cancel out, so we're left that the displacement is just equal to, okay, the electric displacement can equals, let's see, the electric permittivity times the electric field. And to solve for the electric field, that would be 2 pi electric permittivity times S lambda prime in the SI direction. And through the same process, we basically find this electric potential. Okay. So we are told that the inner tube is maintained at a potential V. Therefore, these two potentials must equal the same thing. And using that fact, we can solve for what lambda prime is. So we would have to write everything cancels out. Boom, boom. Well, almost everything. So we are left with the fact that lambda prime is equal to regular lambda over epsilon naught times epsilon. So this is an important fact, and we are able to substitute what the electric permittivity over the permittivity in the vacuum is the free space, and it's basically just the relative permittivity, relative permeability. All right, now that we have lambda prime, let's go back to the fact that the capacitance is just equal to the charge over the potential. So when we look at this, the charge is going to be from the two different parts, with the O and then just in regular air, and that looks like this. Because H will be the distance that the oil moves up, okay, and then we still use lambda prime, and then the remaining, so if we say that the tubes have length L, the tubes have length L, then this distance where the air is L minus H. Okay, and because we just solved for lambda prime, we can plug it in. And I also distributed the lambda with L minus H. And now we can see that we can pull out some stuff on this side, okay? So if we pull out a lambda, we are left with, and we can't really leave our, we could leave our answer in terms of the relative permeability. We are giving the susceptibility, which is chi E, so we can conveniently pull out an H here. And this is what chi E is equal to. So the charge ends up okay. So if we plug into the capacitance equation we have on the top, it's lambda chi and then we know potential, and then simplifying, we have so we were able to find what the capacitance was in terms of H. So now we go back to the equations we used at first, and we would need to take the derivative of the capacitance with respect to H. So the electric force is 1/2 v squared, and then the derivative, so we see, well, this term would just be a constant, and we only have one h, so this is what its derivative would look like. Pretty simple derivative. The 2's cancel out, so okay, so that is what the electric force is, and then let's find out what the weight is. So that's just simply mg, and I mean, we can't really, well, we could know what m is, but we are given a mass density, so we can just multiply that by the volume. So the mass density was rho, and then what is the volume where the oil is? So it's basically the big cylinder right here minus the smaller cylinder. Maybe it's around here. Well, it's over here. So the volume where the oil is, it's the purple cylinder, the area of the purple cylinder minus the area of the small cylinder. And that's times h, the height. So putting everything together, well, we would have the h right here. So going back to this, solving for h will look like this. We would basically just move this chunk to the bottom of this equation for the electric force. I mean, I obviously forgot a g, sorry. And then that is the weight. Okay, so this is basically the height that the oil will rise in the space between the tubes. Hopefully you guys got more insight on how to approach a problem like this. Thank you so much for watching.